Hello everyone, we are solving question 40 of grade 2016 chemical engineering paper, and the question is, in a 1-1 pass shell and tube heat exchanger, steam is condensing in the cell side at a temperature Ts of 135 degrees Celsius, and the cold fluid is heated from a temperature T1 of 20 degrees Celsius to a temperature T2 of 90 degrees Celsius. The energy balance for this heat exchanger is given by this equation, where U is the overall heat transfer coefficient, A is the heat transfer area, m dot is the mass flow rate of the cold fluid, and Cp is its specific heat. Tube side fluid is in turbulent flow, and the heat transfer coefficient can be estimated from the following equation, where N is the Nusselt's number, R is the Reynolds number, Pr is the Prandtl number. The condensing heat transfer coefficient in the cell side is significantly higher than the tube side heat transfer coefficient. The resistance of the wall to heat transfer is negligible. If only the mass flow rate of the cold fluid is doubled, what is the outlet temperature of cold fluid at a steady state? So, in this given question, we have been given a single pass shell and tube heat exchanger. Let's just consider single tube over here, and this will be my shell side. So steam is condensing in the cell side at a temperature of Ts, where Ts is given as a 135 degrees Celsius. Similarly, the cold fluid is heated from a temperature of 20 degrees Celsius to 90 degrees Celsius. So Tc in, we have been given as 20 degrees Celsius, and Tc out, that is the cold fluid outlet temperature, we have been given as 90 degrees Celsius. And then we have been given the energy balance. This energy balance equation, as well as we have been provided this correlation of Nusselt's with Reynolds number and Prandtl number. And from the given, we have been given the condensing heat transfer coefficient in the cell side is significantly higher than the tube side heat transfer coefficient. So the cell side heat transfer coefficient will be based on the outer side of the tube, so we call it this as H0, and it is significantly higher than the tube side heat transfer coefficient Hi, and the resistance of the wall to heat transfer is negligible. Okay, so we can use this later on. And the mass flow rate of the cold fluid is doubled. That is for the second case. Let's just consider M2. C for cold fluid is twice of the cold fluid mass flow rate in the first case. So this is all the information we have been given. So the heat transfer coefficient, we can write it as, for the inner side, as Ui is equal to 1 upon, so this is my convection resistance based on the inner side heat transfer coefficient. Similarly, this will be my conduction resistance to the wall, that is Ai upon K ALM plus Ai upon A0 into 1 upon H0. So this is my convection resistance, this is my conduction resistance to wall, and this we have been given in the question, that is the resistance to the wall to the heat transfer is negligible. So this entire term is negligible, so let's just consider it as 0. And also we have been given this correlation, H0 is very greater than Hi, so that is, we can write that H1 upon H0 is very less than 1 upon Hi. Also this area of inner side area will be less than the outer side area, that is Ai is less than A0. So that is basically, this term will also be very less as compared to this term, so we can neglect this term. So from this overall heat transfer coefficient, we can write this as Ui, 1 upon Ui is equal to Hi. That is, the overall heat transfer coefficient is equal to the heat transfer coefficient of the inner side, that is Hi. Now we can find this Hi by using this Nusselt's number correlation. So let's just do that. So Nusselt's number is given as H, then the inner side diameter into K, and this is written as 0.023 This Reynolds number we can write it as rho Vd upon mu, inner side diameter upon mu into 0.8. Similarly, Prandtl number will be Cp mu by K. Let's just keep it as PR only, and this will become 1 by 3. So we can write this Nusselt's number as 0.023, and let's just change those parameters into mass flow rate terms, that is m dot, so that we can have the correlation between Nusselt's number and mass flow rate, and later on we can calculate the correlation between Hi and the mass flow rate. So by using this density and the velocity, we can change this into mass flow rate as di into mass m dot upon Ai is my outer the heat transfer area of the inner side upon mu into 0.8 into Prandtl number of 1 by 3. So this diameter will remain constant, area of the inner side will also remain constant, mu will also remain constant. Only the variable is m dot, that is the mass flow rate. So from this we can write that Nusselt's number is directly proportional to m dot raised to 0.8. So that is, we can write it as nu is equal to k times m dot raised to 0.8. So that is, we have the correlation between Nusselt's number and the mass flow rate. And then we can use this Nusselt's number as hd by k and write it as hdi upon k is equal to k dot into 0.8. Again, here this h we can replace it by u, as we have found out from over here. So that will give us ui is equal to ui into di upon k is equal to k times of m dot of 0.8. Let's just call this constant as k dash. So here di is also constant, this thermal conductivity will also remain constant, so that is, we can write as ui will become, let's say, k double dash of m dot raised to 0.8. So that is, our overall heat transfer coefficient is proportional to m dot raised to 0.8. So that is ui is equal to k times m dot raised to 0.8. So from the earlier slide we have this information. Now let's just use this equation. Now, so that is, this equation is ln of Ts minus T1 upon Ts minus T2 is equal to UA m dot Cp, and here we know that U is proportional to m dot raised to 0.8, so that is, we can write it as k double dash 0.8 into area upon mCp. This can be written as, again this area and Cp will remain constant, so let's just call it as k triple dash is equal to m dot raised to 0.8 minus 1 will become minus of 0.2. So that is ln of Ts minus T1 upon Ts minus T2 is equal to k dash of m raised to minus of 0.2. So now we have this correlation that we will be using to find the outlet temperature for the second case in which the mass flow rate is doubled. So let's just write it over here. In case 1, the mass flow rate was m dot, and T1 we were given as 20 degrees Celsius, T2 we are given as 90 degrees Celsius, and Ts we are given as 135 degrees Celsius from over here. And in the second case, the mass flow rate is doubled, that is M2 will become twice of M1. So that we found out from here, that's mass flow rate is doubled. Rest all, that is T2 we have to find. T1 and Ts will remain same. So that is, we will use this equation for both the cases to find our T2, that is the outlet temperature. So for case 1 we can write this as ln of Ts minus T1 upon Ts minus T2. This is for case 1. Similarly, ls of Ts minus T1 upon Ts minus T2 for case 2. So this is the term that we have to find, will be equal to K triple dash M1 raised to 0.2 upon K triple dash M2 raised to minus of 0.2. So now Ts we were given as 135 degrees Celsius, so we'll just replace those numerical values. 135 minus 20 upon 135 minus 90 upon ln of 135 minus 20 upon 135 minus T2. T2 we have to find. This will get cancelled out, and M1 upon M2, that is we can write M1 upon M2 raised to minus of 0.2. This is basically, that is we can write this as ln of 115 upon 135 minus T2. This will go over this side, and this will come into denominator. Okay, so this term will become ln of 115 upon 45 into 1/2 raised to minus of 0.2. So 1/2 raised to minus of 0.2 will be 0.8075. This will become 0.93. So this term will become 0.8167. That is ln of 115 upon 135 minus of T2. Ultimately this we can solve. And from here we can solve this and find the T2 as 84.192 degrees Celsius. That is for the second case in which the mass flow rate is doubled, the outlet temperature of the tube will be 84.192 degrees Celsius. So from the given option we can select option B as our correct answer.